Whoop, whoop, whoop. Yeah, audio's working. I think it's working. No one's come in yet, so I'm just waiting. No one's come in yet, so I'm just waiting. Waiting and preparing. You know, I'll just have to cancel, I guess, if nobody shows up next 10 minutes. Oh. Change. Better. Actually, I don't like that. Okay, well, I'm about to go into starting the lecture in about 7 minutes. Maybe me talking will be a little better than this. Wouldn't be the first time I thought to myself on camera like this. Something I do on a regular basis. Time to teach. Okay, it looks like looks like no one's watching me. This is fine. It'll be okay. All right, everybody. I am William Ashe, and this here is my first free Python lecture that I'm offering. I'm going to be doing this same time tomorrow, 6 p.m. Probably going to be doing a duplicate of this one if no one shows up, but otherwise, I'm going to proceed and then post the recording later. So this course actually comes from MIT, Massachusetts Institute of Technology, and they developed this as part of their open courseware project. You can actually go out and get this curriculum yourself. They even have code on GitHub that you can use to set up a complete LMS to serve up this curriculum. But what I'm doing is putting the course documents on a Google Drive. I've shared that on my WordPress blog, netlabwizard.org, and you feel free to go out and find those resources on my blog, and then you can follow along with the course material. There are some practice questions that we're going to take a look at the end of this lecture, but without further ado, I'm going to go ahead and get started and start talking about Python. So the first few slides actually relate to being in the actual course itself, so we're going to be skipping a few slides. Wish I could use my keyboard to say next. So yeah, skipping this because this is just Ash's free course on the internet. So no grades for this. The idea is we're here to learn, and you can have a chance to ask questions. I do have slow mode on, so you can only put a message on once a minute, but that's really not all that much of a limit, really. We should take a minute probably to think about what we're going to type anyways. So this is a fast-paced course. It's 12 sessions long, and in those 12 sessions, you're not going to come out of the course expert in Python, but you'll have a level of mastery of it that definitely gets you started with this programming language. Now, if you want to position yourself to succeed with this, it's important that you try to do the problem sets. The problem sets are available in the Google Drive along with this slideshow presentation if you want to have that. It's very important that you practice these skills. No amount of watching me on YouTube programming is going to make you a great programmer. The best way to learn to be a programmer is to program yourselves. Just like anything, that requires practice, you got to do a lot of it. You might want to download the code before these lecture sessions, and then you'll be able to follow along on your computer. If you have multiple monitors, that would be a great way to get set up doing this. Now, these MITx finger exercises, I don't know what those are, but there are some practice questions available on the MIT website, just little bite-sized quiz-type questions, and I'll direct you to those as well. So let's not be afraid to try out these commands in Python. You might be concerned that you might break your computer by typing in something into Python. That's probably not going to happen. There's been some situations where I've stressed out my computer trying to brute force something in a programming challenge, but for the most part, the computers handle what we're doing in Python very well. And as long as you're not messing with packages that are, maxing out all your threads or something like that, you'll probably be okay, right? So don't be afraid to try this stuff out. Can't break it. So the whole point of this course is, of course, to learn how to program in Python. But as far as why we do this kind of course, there's three big areas here. There's programming skills, like the specific syntax and concepts related to the Python programming language or programming languages in general. There's a knowledge of the concepts. Right? So as we talk through these slides, you're going to learn about some stuff that you might not know about programming. Unless you've taken a course like this, there's just some things you might not have heard from reading tutorials or watching short videos on YouTube. And the last thing that come out of learning Python is to improve your problem-solving ability. Programming is really about solving problems with computers, typically mathematical. But there are so many different ways we can improve operation in our businesses, in our schools, in our homes, if we learn about programming. And also, it's a very valuable skill that you can take with you and find a place in the workforce. So, lots of value to learning Python. All right, the main topics of this course are, there's just a few of them, but these are really big topics. So firstly, you're going to learn to represent knowledge with data structures, okay? So Python allows us to represent different things with data structures, and you're going to learn about these data structures and what they look like and how they behave. We're going to learn about iteration and recursion as computational metaphors. Iteration and recursion are really important structures in programming that we can use to do massive amounts of work in a very short amount of time. So we're going to master those so that we can confidently design those structures. We're going to learn about the abstraction of procedures and data types to understand how we can have these things be abstract but still have them work together. This, depending on how we set up our code, having very abstract procedures and data types allows us to do flexible, cool things with our code. And we're going to see a little bit about that today, actually. I think it comes up probably over and over, time and time again. We're going to organize and modularize systems using object classes and methods. So in this Python course, this beginning Python course, you're going to learn about object-oriented programming concepts. The idea of object-oriented programming has been around for a while. It's not exactly new. And if you want to get into programming, knowing about object-oriented concepts is going to help you go further. So this is an introductory class, but we are going to go into some depth on object-oriented programming, objects, classes, and methods. We're going to learn about different types of algorithms, searching and sorting, which is very typical of a programming class like this. You're going to learn about how to sort data using different algorithms and search for particular pieces of data. And then we're going to have a discussion of the complexity of algorithms, which is very important when you're in computer science. There's different ways of describing complexity of algorithms, and basically you need to know about the complexity of your algorithm so that you don't end up using way too much memory when you go to compute something very large, right? So knowing the complexity of what you're doing is essential. So what is a computer? What does a computer do? Well, fundamentally, it is a calculator, and it does calculations, billions per second even. It can remember hundreds of gigabytes of storage, right? Like, could you imagine if you just remember vast quantities of stuff like that, right? And what kind of calculations can we do with Python, right? Well, there's going to be a few different kinds, right? So there's the type of calculations that are built into the language, so like the essential operations. And then there's going to be calculations that we are going to define ourselves as programmers. So like when we go and write our own functions, we are basically telling a computer how to do something new. Computers only know what you tell them, okay? And you're going to hear that a lot in these presentations. A computer is only going to do what you ask it to do, and sometimes it's what we want, sometimes it's not what we want, and that's the job of the programmer, to try to improve that. So, two types of knowledge here, declarative knowledge and imperative knowledge. And I think the idea is to compare this to how a computer works, okay? So declarative knowledge is a statement of fact. So the idea of somebody winning something before the class ends. And if you watch this lecture video on the MIT website, she actually gives away a Google Cardboard, which is, I think, a VR thing you stick your phone in. It's made out of cardboard. So the idea is like a statement of fact, that's declarative knowledge, right? Reporting a fact. And then there's an imperative knowledge, which is knowing how to do something. So, for example, having the students sign up for the raffle, the teacher opening up her IDE, the teacher choosing a random number between 1 and the number of students in the class, and then giving the Google Cardboard to the number that corresponds to the sheet, right? If you watch the video, she actually does this. But the idea is this is that recipe. This is the ordered steps 1 through 4. And computers can have both of these types of knowledge. They can hold a bunch of facts for us, and they can hold recipes, right? They can hold instructions for how to do something. So here's a numerical example of that imperative knowledge, okay? So let's say we need to find the square root of a number x such that, let's say the square root of a number x is y such that y times y equals x, okay? So let's say y is the square root of x. There is this algorithm for coming up with a square root of a number. So you start with the guess, and maybe it helps to know what the square root is already, but you start with the guess, g. And then if g times g is close enough to x, we stop and say g is the answer, right? That's just the definition of a square root. Otherwise, we're going to make a new guess by averaging g and then x divided by g. So remember, x is this number here. So what you do is you take your number, you divide it by your previous guess, you're going to get another number, and then you're going to average that with your previous guess. So here we have this chart, and so first guess was 3, 3 times 3 is 9, not quite close enough, so then we do 16 divided by 3, which is a little more than 5, right? 5.33. And then we do 5.33 plus 3 is 8.33 divided by 2 is 4.17. There's a little bit of rounding there. All right, and then we take that as our new guess, and then we do it over again, right? And when we do it the second time, we get even closer to the real square root of 16, which is 4. And then, but we're still not exactly there. We do it again, and then we get even closer to 4. All right, so this is a numerical example of that type of imperative knowledge, this recipe of how to do something, okay? So what is this recipe? What are the parts of it? Okay, so the number one thing is a sequence of simple steps. They're ordered, and one thing at a time, we are stepping through this process. The second thing this recipe has is a flow of control that specifies when each step is executed. It goes in order from top to bottom, right? We don't just start off with the last instruction and then go to the first instruction, right? It might seem like that when you're looking at code later and what it's doing, but we actually have control structures that allow us to manipulate that flow. And the third thing is having a means to stop. That's important with these types of processes, right? Let's say you're making bread. Well, you're going to run into a recipe for making bread, and you're going to go through that recipe, and when you finish the bread, you're done. You don't want to just keep making bread nonstop, right? So knowing when to stop is really important. That's a part of this process as well. Now, if you have these three things, these three components, that is what constitutes an algorithm. A sequence of simple steps with a controlled flow that specifies when each step is executed, and then it stops eventually. That's algorithm. So computers are machines. Now, you might not think of it as a machine because the mechanics of that device are so small and so abstract to us, but computers are just tools that have mechanical processes going on in them, electromechanical processes, some magnets in there too. So there's really two different types of computers. There are fixed program computers, and then there are stored program computers. Now when we talk about fixed program computers, we're talking about like your handheld calculators. Now, a lot of you, if you're younger, you might not have a ton of experience with those handheld calculators, but I bet you've used them in school. These types of computers, and they are computers, can only do a limited set of things, like add, multiply, divide. You might be able to put a variable in there, like one at a time. You might be able to store some values in some calculators, but then if you pull the battery out, those values probably go away. Fixed program computers can only run the programs that are built into their memory. They have very limited processing power, and they have very limited things that they can do. Now, stored program computers, these are a lot more flexible. They store and execute instructions, and because we can store new instructions on these computers, we're able to change what they're capable of doing. So just like with your cell phones, right? You can go get a new app, and now your phone will do something totally new, like have a whole new way to message your friends. Or you'll have, you can go get a QR scanner app, and then now you can scan QR codes, right? So our phones are a great example of a computer and how we can store programs on there to, get new functionality. Now, back in the day, computers stored programs on tape, and they were basically a strip of paper with rows of holes punched in them, okay? And I think it's a little more apparent of this storing it in the computer when we think about how it was then, when we had this stack of cards that somebody would actually have to feed into the machine, right? You could see it go in. But when we download things off of a USB drive or the internet, we are storing data in the computer, and that's what gives it the new functionality, right? So we have stored program computers, and our computers are very complicated nowadays. I teach A+ here, and learning about computer components is a massive topic in itself, right? But if we're trying to go into the field of IT, these are things we have to learn about. So here we have an example of the basic machine architecture. This is kind of the model for how our computers work. So we have memory that's here, and this is basically the data, okay? This is where we're going to put our data. That's where we're going to put our data, and that's where we're going to put our programs. All right, so when they say memory here, if you know about computer hardware, it's a little confusing, right? Is this like our hard drive where we're storing the programs, or is this our RAM where it's accessing things, right? Well, these all kind of go together. Okay, a computer's got two types of memory. It's got the kind of memory that it uses for working, and then it has a kind of memory that it uses for storing things. But really, when we talk about memory, the distinction between those two things are how we access that data. Is it right off our CPU, or is it a little further down the bus and a little slower, right? So we use that high-speed RAM for managing the work that we're doing in the computer, and then we use that slower but still pretty fast data storage on our hard drive or M2 drive for storing the applications that we're running. So what we have here is what constitutes our processor. So we have an arithmetic logic unit. This is going to do primitive operations, so things like add, subtract, multiply, divide. This is an arithmetic logic unit. And then we have a control unit, and this is going to help us control where we are in the program, okay? Now, in addition to having this CPU and this memory, which really is kind of a couple different structures in hardware, we have input and output. So input could be, our keyboards and our mice, right? And our output is like our monitor, right? So we have input and output, we have a CPU, and we have memory. That's what makes a computer. So stored program computers have sequences of instructions stored inside the computer. They're built by a set of primitive instructions. There's three things that they do really. We have arithmetic and logic. We have simple tests for testing logic, and then moving data. It's got to be able to do these things. A special program interpreter executes each instruction in order, using tests to change flow of control through the sequence and stopping when it's done. So this is kind of what Python is. Okay, Python is an interpreter, and it's going to help our computers execute the instructions we're giving to it in the proper order, and then stop when it's finished. That's what Python's doing. So talking about these primitive operations, okay? So Alan Turing, the great computer scientist, he showed that you could compute anything using 6 primitives alone. And those primitives were move left, move right, read, write, scan, and do nothing. Okay, just those 6 things. Now what he showed is that you can compute anything with that, and so with that in mind, understand modern programming languages have even more primitives than just those 6. We have a lot more. But if you can if you have a language that has that same number of primitives, or it's basically the same things, and you can write that in one language, right? If you can write a program in one language, then you can write it in any other language as long as it has those 6 primitives at least, okay? So it's pretty great. It's pretty cool. And so Alan Turing, if you haven't heard that term Turing complete, that's that story about, you know, what does it mean to have a programming language, right? What are the minimum number of things that have to be in there? So creating recipes. A programming language provides a set of primitive operations. Expressions are complex, but legal combinations of primitives in a programming language. Expressions and computations have values and meaning in a programming language. So a few different definitions here. We're getting the definition of operations, which are being connected to these primitives that we were talking about, those like 6 operations that Turing described. And expressions are a combination of values with these operations. It's what makes an expression. So often in these programming classes, there will be a point where we discuss how a programming language is similar to like a spoken language, okay? So take the example of English. English is composed of words and punctuation, right? And spoken words as well, and the sounds that we make in our languages. Programming languages consist of numbers, strings, and simple operators. And we just can kind of compare them here, right? All these primitives for Python, and then just a small sample of words in the English language, right? So there's a lot of pieces to these things, languages. Another aspect of language is syntax. So this is a great example. So in English, the sentence cat, dog, boy, that is not syntactically valid. When I say that, it doesn't have any discernible meaning. But if we say cat hugs boy, then you immediately know what I mean, right? And that's because it's syntactically valid. So in Python, we have the same thing. If you have the word hi in quotes and then you put a 5 right after it, that is not syntactically valid. The interpreter is not going to know what to do with that data. But if you say 3.2 times 5, it will be able to compute that immediately. It will know exactly what you mean because it's syntactically valid. So syntax is a very important aspect of language in general, and Python is no exception to that. Static semantics are when syntactically valid strings have meaning. Okay, that's interesting. So in English, I are hungry, that is syntactically valid, but it has a static semantic error, right? It's interesting. And then this example here, 3.2 times 5, that's syntactically valid, but then 3 plus the word hi, there's a semantic error there, okay? Now, it's like I'm close, but not quite close enough. These things are very picky. So semantics is the meaning associated with syntactically correct string of symbols with no static semantic errors, okay? So if it's, what they're kind of saying here is if you didn't mean to communicate something and that's what's getting across because you have an error in the way that you're saying something, then that's an error, okay? So in English, flying planes can be dangerous. Yeah, that can mean a lot of things, right? It's syntactically valid. it's not very confusing statement to make, but I have a hard time understanding what is meant by this sentence, flying planes can be dangerous. In programming languages, things are a lot less vague, right? In programming languages, we have only one meaning. Generally, it's not going to be taken 5 different ways what you're saying when you write a line of Python. But what you write might not be interpreted by Python the same way as you expect. And it's not going to have a bazillion different ideas what you mean. It's going to have it's going to think one way about the way that you programmed it, and that's exactly the way that you programmed it. It might not be what you intend. That's why semantics are hard. It's not really an error, but it's not helping you get your work done. Okay? So syntactic errors, the problems with, the punctuation in English, or, using the wrong preposition, right? Those are examples of syntactic errors, and those kinds of things are easily caught, right? When somebody writes something incorrect or they say something incorrect and you have knowledge of the language, you're going to see that right away. And in Python, that could be, when you miss a quote or a parentheses or you mess up on your indentation. Those are syntactic things and they're easy to catch, right? Once you know how to look for them. Now, static semantic errors, these are almost correct things that people put in, right? So languages are going to check for these kinds of problems, but the error might not be bad enough to actually stop the program from starting. So you can get some unpredictable things happening with that. I see this a lot in Bash scripting, more so than I see it with Python scripting. In Bash, sometimes you got to put quotes in there when you're not really thinking you need to, right? And if you don't put the quotes, then the functions just do really strange things, right? So we end up having to put quotes in there, right? Well, in Python, it's the same thing. You might end up having one of these static semantic errors and get some really unpredictable behavior out of your script. Now, the third category of error here is when you have no semantic errors, but the code is doing something different than what you intended as a programmer. So, for example, your program could crash or stop running. It could run forever. Maybe it never stops. Or maybe the program gives you an answer, but it's not the answer that you expect. Remember, computers can only do what we program them to do. Like, they're not capable of really thinking on their own. Well, maybe some of them out there can try, but that's future stuff and scary, so we're just going to leave it at that, right? So in Python, a program is a sequence of definitions and commands. Definitions are evaluated, and then those commands are executed by the Python interpreter in a shell. Commands instruct the interpreter to do something. We can either type directly into the shell or store in a file that is read into the shell and evaluated. Now, the first set of problems, and these are available in the course resources, you're going to be introduced to both the shell and putting instructions into a file. And I'll take a look at that once we get through the slides. We're getting pretty close. In Python, everything is an object, and programs are designed to manipulate these data objects. Objects have a type that defines what kinds of things programs can do with them. So, for example, Anna is a human, so she can walk, speak English, etc. Chewbacca is a Wookiee, so he can walk, but he goes, does that Wookiee noise, etc. Now, in Python, objects, there's 2 big categories of objects, and this is really interesting. I hadn't heard about this, actually, until this course. They can either be scalar or non-scalar. And what scalar means is that it cannot be subdivided. So, an object that is not multiple pieces, that's a scalar object. A non-scalar object has a structure that we can use to access pieces of that object. Okay, so you're going to learn examples of that in this course. So a summary of our basic scalar objects in Python. The int represents our integers. So for example, 5. Now it also includes negative numbers and it includes 0, right? It's the same definition of integers that you know from math. Float represents the real numbers, okay? So we have positive or negative numbers that include a decimal point. So for example, 3.27. Now 0 could also be a float, but it would just be 0.0 or 0.0. Those are floats. Bool is a type of object that represents Boolean values. Now, if you haven't heard about Booleans, what an exciting moment for you, right? Booleans are true or false values, and we use these a lot in programming. They are very important for helping us organize our procedures, our imperative knowledge, our algorithm, right? And we're going to use those a lot when we get into the next session, which is about iteration, and I think we maybe do conditional statements there. The next type of scalar object is the none type scalar object. This is a special type of object. It has only one value, and that's none. So this is really a useful value. It might not seem very special, but we use this in a few very important spots. So it's good to be aware of the none type. Now, if you're curious what type of object something is, we have a special function called type, and this is going to be able to tell us what we have. So for example, if we put 5 into there, just like this, type, left parentheses 5, right parentheses, when we hit enter, it says int. When we put in 3.0, it says float. Okay, so that's a really useful function, and I think you're going to have a chance to practice that in the problem sets. We also have what are called type conversions or typecasting functions. Okay, these functions can convert an object of one type to another. It can't always convert one object into another, but it will try. So this is something you're going to be able to use. So for example, float with an integer 3 inside. It's going to convert the integer 3 into float 3.0. This function is just intelligent enough to know that it can put a decimal there and a 0, and look, now you got a float, right? Now, integer has a similar function here, but because integers don't have the decimal component, right, the rational piece, because it doesn't have that value after the decimal point, when we use this typecasting function int on a float, it's going to truncate that number down to 3. This is not rounding. If we were rounding here, we would have taken 3.9 and brought it up to 4, right? This isn't doing that. It's truncating. It is simply cutting off that decimal piece and throwing it in the garbage, okay? So those are two examples of type conversion functions, also known as typecasting. We also have one for strings. You can take a number and turn it into a string. I think you could try to take a string and turn it into a number. That only, I think, works if numbers are what's in your string. So we're going to practice printing to the console next. So I'm just going to pull that up. So this is an IDE called Spider, and Spider is available for free. It is the Python package for scientific studies. So it's really great. Now, what we're going to do is, I'll just do a new file. I have something else open. Okay. So I have this new file here, and I'm going to work in two different places here. Okay, so if I'm trying to print to the console, we need to be aware of if we're actually printing or if we're doing something else. edit. Where's my preferences? Tools. Ooh, preferences. There you go. That looks a little better. Okay, so if I just put some math into this right side here. So this is my shell, okay? And if you've used idle, which is the development environment that is packaged with Python originally, I can pull that up actually. Idle is pretty good as well, and with idle you get something that looks like this. This is what we call the shell, okay? And I can type commands into this. 3 plus 3, and it tells me 6. Okay. Well, in Spider, we have that same functionality. It's right here. So 3 plus 3 equals 6. So you see it popping up on the screen. It's important to understand that this isn't actually being printed to the screen. It is simply telling me the result of what I just put in as a way to help me understand what's going on. Okay, if I were to do this instead, which is use the print function, 3 plus 3, notice that it doesn't say out 1, it just says what I wanted to print, okay? And this is because I'm actually printing it at this point. Here, I have the same number next to out. It's showing me this is what's coming out, but it's not a real output, okay? That's important to understand. Now, if I'm over here, I can make what's called a script. So I can put in this script, 3 plus 3, right? And I can save it and run it. And nothing happens. Okay, nothing's happening because I don't have any output. Now, if I actually put print around it, now it tells me 6, okay? So that is a relatively important concept to have down, okay? When you're working in the shell, you might see some output from stuff that you put in, but you're not actually printing to the screen unless you have a function that specifies you're going to be getting output. So that's what they're just telling us here. And it's kind of, there's a little bit of Anaconda, or yeah, they're going to mention Anaconda, they're going to mention Spider in these slides because this is what the teacher for the course, Anna, used for teaching this originally. So to create expressions, we're going to combine objects and operators. An expression has a value, and that value is going to have a type. Syntax for a simple operation would be object, and then an operator in between them, and then another object, okay? Actually, I have a cool old book. Where did I put that book? Here it is. I actually found this in a pile of books that were getting thrown away. It's Computer Approaches to Mathematical Problems, and they explain kind of what we're seeing in this right here. So when you see those angle braces around things, that means we're going to substitute something in there, okay? And you're going to see this kind of syntax and talking about computer stuff. You're going to see this in a lot of different places. Like if you're working in Linux, you might see this in a man page, for example. So building expressions is easy. You got a couple objects, you put an operator between them. And it's more complicated than that, but that's just what we're calling it. So we've heard about operators. Now let's talk about them specifically, okay? So we have the plus symbol, okay? That is going to give us a sum. So I plus j is going to give us the sum of I plus j. If we have a minus sign, that is the difference, and that gives us subtraction, basically. We have a star or an asterisk that indicates multiplication, so that's how we get a product. And then using a forward slash, we get division. Now there's one more, and that's a double forward slash. That's a kind of division, but it's subtly different. So here we're just not quite talking about the double slash yet. So with these up here, there's a little bit of a weird thing that happens, but it makes sense. So if we have two integers and we add them together, then that result's going to be an int, right? But if one of those numbers is a float and we add a float plus an integer, we're going to end up getting a float out of that. And this should make sense. If one of the numbers has a decimal, then now we're going to need a decimal to accurately represent our answer, right? The product or the sum or the difference. Now with division, the result is always a float, and that's built in. So even if you have two numbers that divide evenly, like 10 and 5, 10 divided by 5 will not be just 2, it'll be 2.0. And that's because that's how division works in Python. Now a couple other operators here. We have modulo, okay? And modulo gives us the remainder. It's a remainder function. So I modulo j is going to give us the remainder when I is divided by j. Now a double asterisk, that gives us I to the power of j. So 2 star star 3 would be 2 to the third power, which is 8. So Python also recognizes parentheses, and it's probably a lot better at parentheses than most people are. So if you're struggling with the way your code is working and you think it could be parentheses, yeah, Python might be catching something that you're not. So parentheses are really helpful sometimes, but they can become a little complicated to work out. So yeah, Python understands parentheses really well, and it's going to do anything in parentheses first, just like you learned in school when you learned PEMDAS. P is for PEMDAS, or for parentheses. P is for parentheses. Without parentheses, then we do exponentiation, and then after exponentiation, the double asterisk, we then have multiply and divide. Now multiply and divide happen at the same level of precedence, okay? They happen in order from left to right. So this is vitally important because division is not commutative. If I have 12 divided by 3, that's not the same thing as 3 divided by 12. So it's very important you work left to right with your multiplication and division. And the same thing with adding and subtracting. You need to do adding and subtracting left to right as they appear in the expression. Now, Python has no problem understanding this order of operations, but people have different meanings that might not be congruent with the way that computers understand order of operations. So if you're getting a number out that you're not expecting, you might need to take a look at, your operators and think about the order of operations. Now, we always are doing the same thing in Python, and that's binding a variable to a value, okay? In Python, you're always going to have a variable on the left side of the equal sign, and you're going to have a value on the right side of that equal sign. Okay, that's always how it's going to be. In mathematics, sometimes you have a variable on the right and some numbers on the left, but in Python, it's never like that. It's always variable on the left, value on the right. The value is going to be stored in computer memory, and that variable is going to be bound to that value. Okay, now we can retrieve the value by now using the name or variable typing it in. So let me show you that in Spider. So I'm going to go here and I'm going to say var equals 30 and hit enter. And now Python knows what var is. Okay, I can get it to tell me by typing in var and hitting enter. It tells me var is 30. Okay, remember that's not really output. If I wanted output, I would need to put the print command in, and then now it's proper output, right? Now you can have all kinds of data in here. I can say strng equals my cats are the best. I do have really nice cats. They're great. And then I can now print. I can print my string. And we'll talk about strings. I forget, we hadn't mentioned strings yet, but that's just another type of data. Strings are an example of data that is, if we go back to the presentation, non-scalar. Okay, so strings are non-scalar. Each letter actually is a subdivided piece of that larger object. Okay. But anyways, we can use these variables to invoke a piece of data by their name, right? So why might we give names to the values of expressions? Well, we do that so that we can reuse values over and over again. Also, it makes it easier to change things later. So here's the example of calculating the area of a circle. So area of a circle is pi r squared. So you say pi equals 3.14159. That's just the first 5 digits of pi there, right? And then radius, let's say the radius is 2.2. Area is now going to be pi times, or radius to the second power. Remember, double star is exponents, right? So what we have here is a procedure for calculating the area of a circle. So I might as well do that, right? So I'm just going to do it, well, Windows 11 is always trying to make my life easier. It's a long thing getting in the way. Okay, so I'm just going to type it in. Pi is equal to 3.159. And that's about 3.1459. Radius, we're going to say is 2.2. And then area is this value of pi. It's not actual pi, right? It's not nearly accurate, but good enough for a simple calculation. Remember in elementary school, we always used 3.14, and then our answers were just really rough, right? You can't use that in a lot of kinds of engineering. That wouldn't be enough significant digits, right? So pi times radius to the second power. Now I need to print area. So if I run this, here is my answer. Forget, you guys are having my head block some of the screen. Okay, there it is. So we can see the area right here, okay? And it got to there because I have these values that I'm storing in these variables, and one line at a time, I'm using operators on these values on the right side of that equal sign. Notice there's no operations happening on the left side of that equal sign, right? The equal sign is for assignment. It's for binding expressions to variables, binding expressions to these names, okay? That's just the way that it works. There's no messing around with that. now this slide is just kind of showing us how this could get a little bit more complicated. So like, let's say we wanted to go at the end here and now say radius is equal to radius plus 1. Okay, well what that's going to mean is radius is going to go from being 2.2 to being 3.2. But that isn't actually going to affect the value for area, right? And the reason why it's not going to affect the value for area is because we already calculated area with these two values when those two values were these values that are bound up here, right? But when we go here and we rebind it to its value plus 1, that means that value is different, and we no longer have access to that previous value of radius. It's gone. We've redefined it, okay? If we wanted to see that updated area value, we would then need to have another line that then calculates area again, all right? And we can do that right here. So hopefully my head's not covering this. So I have my radius is 2.2, I have my area calculated, and then I'm going to print area. Next, I'm going to say radius is equal to radius plus 1. And then I'm going to print area again. And you'll see that the value that's being printed will not change. I'm going to actually, yeah, I'm just going to leave it at that. So what we should see is just two more 15.2s pop out of here. See, they both come out exactly the same. Now if I take this line here, the area line, copy it, and then put that here, now we should see two different values of area come out. See, when I change that radius by 1, I actually increase the area by a lot, doubling it actually, right? But that's just how circles work. So programs only know what we put into there, okay? And we only are binding variables on the left to expressions on the right side. That's how it always works. Now, sometimes your code is going to go over multiple lines. That might be it actually going over multiple lines, or it might just be the word wrapping of whatever IDE you're in. Okay, but generally you only have just a variable on the left. That's how that works. When we took that value and we changed it, we rebound the variable name using that new assignment statement. That previous value may still be stored in memory, but we no longer can get to it. When we go and add 1 to it and call that radius, now Python has access to only that value of 3.2. It no longer has access to that 2.2. Okay? And that area hasn't changed unless we were to add that additional line like we did in Spider. So that's actually it. So that concludes the lecture slides. So what I'm going to do next is open up the problem or the code that comes with this lecture and just show you a couple things for you to try out. And then I'm going to conclude this because it's time to go home. So this is lecture 1.py. This is the file that's included in the folder along with the slides, the PDF slides. So you can see here, print area. It's all been done for you. It's an example here. And again, this is just what we just did. All right, now here we're getting some hints about how to use commenting and uncommenting in this Spider IDE. So sometimes you're going to want to comment large segments of text. So we're actually getting a shortcut for this. So in Spider, you can select all the lines that are commented, and if I want to uncomment them, I can just do Control 1. and now they're uncommented. And if I want to comment these lines, Control 1. Now they're commented, right? So we use comments for explaining what we're doing in our code. You can either put it on a line by itself, or you can go after your code and you can say things here. And that's called an inline comment. Now, inline comments are kind of considered not stylish, right? It's not good Python style, but sometimes the inline comment is helpful, and you might use that when you're debugging or something. Okay, so I'm just going to comment this for now. Control 1. All right, we also have autocomplete in Spider. Okay, and this is really good to know. So here is a very long variable name. Don't name them this long, please. Okay, that's a huge variable name. In Python, you want to have descriptive variable names that are self-documenting. So the idea is you can read a variable name and you know exactly what it is we're talking about. There's some conventions with naming variables that you need to know. Like you can't begin a variable with a number, right? You can't have spaces in your variable names, and there's no special characters allowed but underscore. And that's basically the definition of how to make variables. So with this very long variable name, I can actually use tab completion in Spider. Not every IDE is going to have tab completion, but this one does. So I go to type it in, A_VE. Oh gosh, this is too long, right? But you can see it right here. It just popped up, and I can actually press tab, and it finishes it for me. Okay. Now let's rebind that very long variable to that, and then let's print that very long variable. See, it prints 10 because that's what I just set it to. So I'm just going to wrap this up by going back into the Google Drive and showing you what's in here. So this is the folder that's shared on netlabwizard.org. So I guess I might as well pull that up. netlabwizard.org. Here's the IT for Everybody link. Here's the link to this stream. If you were watching it live, I was hoping you would click on that. I don't think anybody clicked on it. So you can click on that link to get there. If you want to get to the course resources, that's this one. Okay, so that gets you to this PDF folder. Inside there, you're going to find this style guide, and this is a wonderful document that was provided with the course. It explains how to write well-formatted Python code. This is stuff that might seem kind of heavy right now, but as you learn more, this will give you some great advice about how to write good Python code. There's some newer style guide stuff out there. There's some, they make small changes to Python from time to time, and this course is a little old, but I think we're only a few years old, so most of it's going to be pretty accurate with what's the industry standard right now. Now, the homework problem sets are right in here. So we got, they're zipped folders, so you're just going to find it from there. I don't know why I got this in there. I'm just going to move it to this folder because I think I did that because for some odd reason everything was zipped except for PS1, but PS1 was just a PDF. So I think these other files, if you actually go into them, there's a PDF plus several Py files, whereas in this one over here, it's just a single PDF. You don't have any files you need with it. Okay, so here are the problem sets, and I'm not going to release those slowly or anything because I want you all to have access to this stuff. So it's all there. And lastly, before I go, I'm going to leave this full stream up here. I'm not going to edit it, so if somebody comes across this link and wants to watch what I just did, if that's you out there, thank you. Thank you for watching this because I took the time to do it. I have a link here that says donate, okay? I've been going through some hard times. I'm trying to raise money to get more time with my kids and to help me get out of debt. If you could please click on this link or share this story, I would appreciate it. I've been looking for hope the last couple years, and it's been really hard. It's hard to find hope out there. So part of the motivation for doing this online is to just try to get out there more, increase my social network, and maybe somebody out there would like to support me in producing more content. That if they donate to my cause on my GoFundMe, I'll definitely be encouraged to produce more content for the world. Also on my blog, I have some Python tutorials that I've written. There's actually an additional one. I haven't linked it here properly, but it's right here. I have 2 lessons basically, and this is based on how to think like a computer science series, and it's basically me discussing the stuff we're learning about, but more in my own words. Okay, so that's fun, and if you all could visit my blog and leave comments if there's something interesting to you, that would be really great. Also, you can read about me on my blog. If you're curious, I work at Job Corps. Job Corps is a free training program for disadvantaged youth. If you're between the ages of 16 and 24 and you would like to get trained in IT, please consider joining our program. It's absolutely free to students and their families. There's no cost. There's no bill that you get later. And we can get you some really awesome certifications. Not just IT, we also do construction trades. We do professional stuff, medical. It's an awesome program. And you can go to jobcorps.org to learn all about that. So that's it. Thank you, everybody. I appreciate it. And again, if you could donate or subscribe to my YouTube channel or all those things that you people do, I'd appreciate it. Thank you, everybody. I'm now going to end this stream.